All right, everyone, welcome to ECE 20002 for today. As I kind of mentioned a few seconds ago to the in-person class, today's lecture is going to focus on preparing for exam 1. My goal is not to talk about any of the new material from convolution in lecture set 3, just review as much as possible and answer some student questions. We didn't get as many Piazza posts as we like, asking for things to review, so hopefully we'll get some things here. So I have a few things prepared, not many. We'll see how far we get. I do want to say, looking at the feedback from the so-called practice exam and survey, where I was asking you your opinions on what to do differently with like quizzes and homework or lectures and office hours, the refrain for what to do differently in lectures is more examples. Like that was kind of an almost universal thing. To which I was like, I thought I was doing a really good job with examples. And some people were even more specific, and they say they want, more examples worked out or more examples of number. Some people wanted examples worked out in real time. I will say that one's unlikely to happen. For those who want more examples of real time, you can still ask for it in your feedback. That's fine. Just because we have, so many people participating asynchronously, where they watch the videos after they've been posted on Brightspace. It's one thing, I don't really have a good webcam set up or an area set up where I can work out problems like, by hand. And I'm certainly not going to do it, sketching with a mouse. I don't have like a Wacom tablet or anything like that. So you can watch me live code LaTeX, or you can watch me work things out by hand. Either of which is kind of problematic. LaTeX, you have to compile it periodically to make sure you're getting the right answers, and it shows up properly. And for working things out by hand, it's a little unfair for the people who are watching a recording. You might have to pause on the exact right frame in order to see something. People live can be like, hey, your hand is covering, equation on the third line, whereas people who watch asynchronously wouldn't be able to do that. So yeah, feel free to keep, doing that practice exam. Give me more feedback on what you'd like to see differently in the class and how we can help you learn better. That is why the teaching staff is here. Okay. So without further ado, let's go ahead and answer, first of all, Tianyuan's question. Can you go over exam 1, summer 2021, question 1? So let me bring that up. Exams, exam 1. Then it's summer 2021 solutions. Oh, it's that problem. How do I make this full screen? Nope, that's not what I want to do. Wrong tab. Technical difficulties, everyone. One moment. Let's go ahead, share screen. Okay, so let me just answer this once and for all. So here was the summer 2021 exam. So as you can see, it's got the sort of simple op amp here that we talked about, part of chapter 7 of your textbook, where it's got, this current mirror feeding this differential amplifier stage that's current mirror loaded. Then it's got this common source amplifier stage, and then this common drain amplifier stage at the end. And then part A is asked, find the currents through Q2 and Q4. Okay, not too bad. Then find the voltage gain of the differential amplifier stage. Now, this is a current mirror loaded differential amplifier. I think this question is not fair to ask based off of what we covered in the summer 2022, section of ECE 20002. We didn't talk about differential amplifiers, so other than to just say, hey, this provides, some, differential gain, but, very low common mode gain to provide common mode rejection ratio. That's about the extent we talked about these kinds of things. So asking it in itself seems a little unfair. And the fact that it's current mirror loaded, this is a 4-transistor circuit you have to analyze in isolation. Really hard. Even when I did this in my electronics class, we were starting to use simplified models for our transistors rather than use, the full, full small signal models. The short answer, Tanyan, is you won't see anything like this on the exam. I don't think it's a fair question to ask. You would have to, go through all the work. But we could ask something more like the other two questions, which like the gain of the common source amplifier or the source follower stage. I think those would be more fair questions to ask if we were to ask a question like this. So they do this really complicated circuit where, we do some current steering, and then we get you this small signal model where they use independent sources instead of the dependent source symbol, which is confusing in itself. But this is how it works. And the dependent source disappears over here by something called the source absorption theorem, which is when the control voltage appears across a voltage control current source, you can replace it with a resistance that's 1 over its transconductance. And then that's in parallel with its own output resistance. Like this is kind of awful. And it's dealing with the early effect, which 4 resistors in the early effect is a lot to deal with, but it's hard. The common source amplifier stage, where it's like minus GM, RO, parallel RD, and parallel of RL, you should be able to work that out and figure out how you arrive at that answer. And, again, they use the formula for GM that is equal to square root of 2 times Kn times ID8, where that's the drain current of that transistor. And then, these output resistances are from the early effect. So it's the early voltage over the respective drain currents. This is a fair question. And then the source follower stage has this formula for gain. Hopefully we can look that up in our equation sheet or find that out by our small signal model. If you're wondering how we get these, RD and RL, let's see if we go all the way back to our circuit, which unfortunately they didn't copy it into the actual solution document, so I have to go back. We see that Q4 is our transistor right there. That is acting as a common source amplifier. It sees as its output the output resistance of Q8 as basically its drain resistance, and its load resistance is basically its own early effect resistance. And these resistances appear in parallel with respect to ground, because if you do the common mode equivalent circuit, or not the common mode, the small signal equivalent circuit, all these sources become tied to ground. Maybe I made things more confusing than less confusing. If so, please let me know. Speak up if you would. How do I get ID8? Let's see. So by current steering, the current that flows through here is, equal to the current that flows through Q4, its drain current, is the ratio of the aspect ratios. So it'll be 12 over 0.6 divided by 60 divided by 3. That is times I ref. And they tell you I ref is equal to 1 milliamp. So if I do 12 divided by 0.6 divided by 60 divided by 3, it turns out to be 1. That's convenient. So basically 1 milliamp flows through here, also flows through Q4 is drain. So that comes from the current steering, or the mirror ratio of the current mirror, which is an equation on your equation sheet. Also something we talked about in chapter 4, I believe. Or maybe it was chapter 3. Regardless. Does that answer your question, Tianyan? Okay. What is Q2, Q3? On the same exam, Aubrey? The MOSFET. Oh, it's basically saying it is two MOSFETs in parallel. So MOSFETs that have their source and gates tied together, and their drains also tied to the same place. So these MOSFETs are in parallel as much as you can put a 3-terminal device in parallel with each other, so that the drain current through this acts as though there's a single MOSFET with twice the aspect ratio. That's the idea. I mean, Jarrett, if you're given the formula on the equation sheet, you may use this and say, hey, this is, from equation sheet. It's one of those things where if we say, show your work or derive the equation, we expect you to start, from more or less first principles. So that'd be like the drain equation, or from the constitutive equations or something like that. But, if it doesn't say, you can use the formula sheet. Now you have to be careful. Some of those formulas on the formula sheet were derived for slightly different circuits than the ones you might see on the exam. So you have to, exercise judgment of, can I use this equation as is, or do I need to make some modifications? So be warned, especially with MOSFET circuits. You're welcome. AJ asked, can we go over input-output resistance of amplifiers? Can never really tell which resistors to factor into those calculations. Let me open lecture set 1. Go to 9. So this is the slide that, again, tells you how to form the small signal equivalent circuit. If you're one of the people that received a note on your homework that says you need to review small signal equivalent circuits, this slide is one that you should stare and ponder at for some time. And then obviously you go back and look at some of the previous slides for, the different models and how to use them. Slide 70 also has a review of the important equations. So for example, that equation that shows up time and again, where it's like GM is equal to square root of 2 times, KN times ID, it's right here. So again, this table is a really good summary of the type of equations you need to answer, circuit type questions with DC MOSFETs or AC small signal MOSFETs. So, okay, say we have the common source amplifier. Now, again, this one is kind of almost too easy to say. It may not be informative, but you draw your small signal model, and then you look into the source and you say, you look into the gate and you ask gate, what resistance would you say if I put a ohm meter at your location? So if I were to inject a little bit of test or put a voltage across you and measure the current, what would the ratio of those two be? And since it's an open circuit, it would say, well, you're going to get infinite resistance, not zero resistance, infinite resistance, because no matter how much voltage you apply between the gate and the source, you'll always get zero current flowing. So, arbitrary voltage divided by, zero current, infinity. Now, if we ask the output characteristic, so the output resistance looking to the left of any sort of coupling capacitor. So maybe if we look here and we say, what is the output resistance looking to the left of CC2? Well, we would have to draw our small signal equivalent circuit. It would look something like this. So this empty node right here between RD and RL was where CC2 was. We look to the left and we would say, okay, what resistance do we perceive? Now, when we measure resistance, we turn off all of our voltage sources. So we would turn off Vsig. When we turn off Vsig, that's basically saying ground, 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 ground. So VGS is equal to 0 volts. So that means this right here is applying a current of 0 through this node, which is, again, an open circuit. So we get to say this dependent source is off because, its control voltage is 0, so it's applying 0 current, so it's an open circuit. So when we look to the left of where CC2 is, we would just perceive RD in parallel with RO because both are between that node and ground. So that's how we get this output resistance by inspection. Similarly here, we had two biasing resistors instead of just, feeding directly into the gate. So because of these biasing resistors looking to the right of CC1, we would see RG2 going to ground and RG1 going to VDD gets replaced with a short circuit to ground. So we see RG1 parallel RG2. Oops, you with me so far, AJ? Okay. So let's look at a more complicated example. Let's see, we did that. It's about the same. Okay, let's look at the common drain amplifier. So the common drain amplifier, let's say we're here at CC1 and we're saying, what's the input resistance looking to the right of CC1? Well, we'll use the equivalent T model here. Now you might say, well, wait a minute, we're going to see RG for sure, but aren't we also going to see all these other resistances? And the answer to that is no, because all of the current that flows down through the drain branch of our equivalent T model also flows down through the source branch of the equivalent T model. So because the amount of current is the same, you must have 0 current flowing into the gate, right? Because I is equal to I. That means by Kcl, there must be 0 current flowing into the gate, as we would expect. Because of that, 0 current means, hey, like we said, that's equivalent to an open circuit. So it's like this part is detached from the rest of the circuit. The only reason we draw the line here is because it allows us to calculate the voltages easier. So that means when we look to the right of CC1, all we see is RG, this resistance. Now, what about the output resistance? Okay, so we're going to look at CC2 and look to the left of CC2. Maybe it would say that. Maybe it says look from the left of where V out is defined, in which case we would just add RL and its series or parallel combination. But for now, let's just say output resistance is defined as to the left of CC2. Well, you have to draw your small signal equivalent circuit correctly. That's the number one thing you have to do. But you'll do that and you'll see, okay, we'll have RO goes from that node where CC2 ends to ground, RS node where CC2 ends to ground, and then we have to do something with this 1 over GM because it's connected. Now, because the same current that flows through the resistance also flows through here, it's almost as if the other end, this top end of the 1 over GM resistance is tied to ground. Because the same current must flow through here as through there. It's almost as if it's tied to ground in the absence of any, source. because again, we turn all our sources off when we find equivalent resistance. So by inspection, you could say we see RO, which is from that node to ground, RS, which is from the node where CC2 connects to ground, and 1 over GM, which is, follows the same thing. So they would all be in parallel, RS parallel RO parallel 1 over GM. Now this is where we have to be good engineers and state something about what we know about these resistances. RS is usually in the kilo ohms. RO is usually in the tens of kilo ohms, close to a mega ohm. And 1 over GM is going to be probably in the hundreds of ohms range. We might give you some nicer numbers than real life. But, real life, it's in the, tens or hundreds of kilo ohms. So because it's smaller, the smallest resistance dominates in parallel, so it's about equal to 1 over GM. Still with me? Do the coupling capacitors exist to define RO and RN? They don't exist just to do that. They exist to allow AC signals to be injected into a circuit that's DC biased without disturbing the DC biasing. However, it's convenient to define input and output resistance from those points. In this case, where it's a current-controlled current source, yes, there would be no resistance associated with it, because it injects the same amount of current as passes through this resistance right here. Let's do one last case, the common gate amplifier, because this is another tricky one. So here, let's say we want the input resistance looking in to the right of CC1. We draw our small signal equivalent circuit correctly. That's the hardest part for some people. When we do that, we see, okay, we have this node, which is tied to ground. We have 1 over GM and RS. We could just, look this around, and we'll see that the input resistance is RS in parallel with 1 over GM. Similarly, if we look to the left of CC2, all we see is RD. Could you answer Aubrey's question again? Do the coupling capacitors exist to define RN and R out? No, they are there so that you can couple a AC signal into a DC bias circuit so that you get an amplification behavior without disturbing the DC operating point, the Q point of that circuit. That's why the capacitors are there. Allows us to separate our DC analysis from our AC analysis, as much as we can, at least. However, they are convenient points for defining R in and R out, so that's often what you will see them used. I mean RO in the previous example. Hopefully that answers Shenjuan's question. Tianyin, is it always safe to move the node of RO using the T model? As long as they're at the same potential, you can do what I did with the source follower, where, normally the resistance would appear between the drain node at the top of the page and the source node right around here. However, because they're at the same potential, I could just flip it around and draw it down there to make it easier to work with. For the common gate amplifier, I would not be able to do that because it would be attached to the drain node up here, and there would be other resistances. So it's attached to the V out potential, and I can't flip it around. Does that answer your question, Tianyin? The potential across 1 over GM is the same. Yes. It it didn't modify the rest of the circuit at all. Is it always the truth? No, I showed you that you can't do it for the common gate amplifier because it's not at, you can't move it anywhere else because there's no other node at the same potential. So you wouldn't be able to move RO if you were to analyze the circuit with RO. Little r sub O, I should say. Okay. Any questions about input resistance, output resistance? I did it the easy way every time. Now, the hard way is to actually calculate it using input and output, apply an input voltage, measure the output current. If you want to see me do it that way, I have other slides that I can pull up for that. Do we have any other questions about things we want to see?
I actually had a quick question about fall 2019 exam.
Okay.
Question 5 in 5C, they draw an equivalent circuit, and it's a common gate amplifier, and
Yep.
in the TA's drawing, between source and drain, he has GM-VGS in parallel with RO. But in our textbooks model, they just say because little RO is pretty close to infinity, they just don't even draw it. So should we leave it out or should we leave it in? If you pull up his solution, you can see what he drew.
Fall 19 exam 1 solution. Oh dear.
It's like most of the way down. There you go. That.
Where RO is up there. Yikes. And they use the hybrid pi model. So yeah, this is correct. Canonical ECE amplifier properties. So the input, yeah, how do they even get the output resistance? They just say it's 3 kilo ohms, even though it's not. Okay. They made an approximation here that I don't like. Because RO would exist because they say lambda is a non-zero value. So I guess the question is, do you want me to explain what they did, or do you want to know how you actually solve this type of circuit with RO included?
So if lambda is a non-zero value, then you do include RO, but if
Yes.
Okay. That makes
sense. It's
sense.
not an open circuit.
Okay.
But, how they used it to answer the questions is wrong.
I see.
They had you, draw the circuit with RO, little r sub O, but then they just completely ignored it when it came time to compute the input resistance and the output resistance, which is wrong.
I see.
So you would, if you were me, I'd say you'd have to make an assumption where it's just like, our little r sub O is, so, it's is insignificant compared to the other resistances in the circuit. Like you would have to say something like that.
When you say insignificant, you mean like so large that in parallel it doesn't appear? Right.
Yes.
Okay.
That's what I meant by insignificant. If you're really, really curious about how you would solve it the true way, you have to go to lecture set J3, one of those imaginary numbered lecture sets, and then you go to common gate amplifier redux, and then it tells you how you include RO in the small signal equivalent T model. So this is on slide 25 of lecture set J3 for those who are super curious. And then it says, okay, we're going to apply a test voltage Vx and measure the test current Ix. And then, we can say, okay, this forces GM-VGS down. This is going to be by Kcl Ix plus GM-VGS, and then by Kcl, this has to be Ix. So you do a whole bunch of work, and you get that Rid is equal to little r sub o plus RL over 1 plus GM RO, which is a lot more complicated than just saying it was equal to RL before.
I see.
And then you can make various stages of approximation. And the output resistance is a little gnarly too. Oh, yeah. I was afraid this is what they were asking you to do. And in fact, if you were to solve it like, without making approximations, this is what you would have to do. But this is the slide I was going to show anyway for how you would, deal with, okay, I can't figure out the circuit by inspection. Maybe the dependent source is throwing me off. This is how you apply a test voltage source, measure the test current, and then get your answers.
All right, thank you.
You're welcome, Aubrey. 2019 problem 2, exam 1. 2019 exam 1, problem 2. Okay. Dun da da. They give you an IV characteristic, specifically drain current versus VDS, and they ask what type of MOSFET this is. So the first thing we can figure out is whether it's enhancement type or depletion type. And because there is a curve that is non-zero, it doesn't just ride along, the axis. There's a non-zero curve with VGS equals to 0 volts. That tells us immediately that it is depletion type. There is a built-in channel that allows drain current to be conducted even when we're not applying a control voltage. So now whether it's N channel or P channel, the key is to look at the tick marks for VDS. Normally we would plot ID versus VDS positive. If it were a N channel device, but since it's a P channel device, we need negative values here. So because, or you would plot positive VSD values, which is equivalent to plotting negative VDS values. So this is a P channel depletion mode device, option C. So write the letter correspond to each of the following quantities regions for this device. So VDS in saturation mode. It's the saturated value of VDS. That would be B. So this is the VDS that determines saturation mode. It's the semi-parabolic boundary. Saturation region is where the ID curves level out. So that's region D. Conversely, the linear ohmic region, or triode region, as I like to call it most of the time, is region A. Now, here's tricky. Where's VGS less than 0 or VGS greater than 0? This is where I'm going to use my words when it's a lot easier to use equations. So for an N-channel enhancement type device, you would have VTH greater than 0. And you would have, VGS greater than VTH in order to turn on. That's for an N-channel, enhancement type device. Now, for a P-channel device, you need to have VGS less than the threshold voltage in order to turn on. And as VGS gets less and less than the threshold voltage, usually going into the negative voltages, so the magnitude gets greater and greater, the voltage would, the amount of drain current you get in the saturation region would go up. So because this is a P-channel depletion type device, as we make VGS smaller and smaller than the threshold voltage, we get more and more drain current. So given that this is 0 volts for this curve right here, this curve C is where VGS is less than 0. Conversely, as we bring VGS greater than 0 and closer to the threshold voltage, we would get line E where if we have a smaller drain current. Notice that this is P channel and depletion mode. So P channel device, that's enhancement type, we expect a negative drain voltage. But since it's also depletion type, it's a negative voltage for the threshold voltage or a positive threshold voltage. So VGS greater than 0 but less than the threshold voltage is line E. And line F, well, we didn't talk about that, but that'd just be cut off if that were an option here. Whoops. With me so far, Keaton? Does that make sense? Now, do you want to talk about the next few parts, 2C through 2F? Sure. Okay. So for 2C through 2F, we just use this MOSFET right here. So first of all, we got to identify this device. The arrow is pointing into the gate line. So that means it's a P channel device, and we have this thick bar that represents a completed channel at 0 bias. So this means this is another P type depletion or P channel depletion type device or depletion type PMOS. Lovely. We got to deal with the early effect too. So compute VDS and ID given Vx equals 1 volt and Vy is equal to 3 volts. So first thing you do is label the terminals. This right here is going to be, where the Ix is pointing into. That's going to be equal to Vg. The terminal with the arrow is Vs, and then the bottom terminal where Iz is pointing is Vd. So VDS, well, we can say VDS is equal to negative Vz, which is going to be equal to, negative Vy plus Vx. So negative Vy is negative 3 volts plus Vx is 1 volt. So that we get negative 2 volts for VDS. ID is the drain current, what current flows down the drain. Remember, drain current is always positive by the conventions I have laid out in this class. So at the very least on all of my exams, you should only have positive drain currents. And that's by convention. Or are there 0 if it's in cutoff mode? So 0 or positive drain currents. That's the rule for how I have laid out the sign conventions for the MOSFET. So the drain current would be using the early effect. We have to check the threshold voltage to make sure we are what mode of operation we're in. So what is VSG? VSG is negative Vx or negative 1 volt, which is less than our threshold voltage of positive 2 volts. Positive because it's a negative of a negative, because we expect negative for being P channel, negative for being depletion type, so it should be positive 2 volts. So because Vx is VSG is that, so VGS, if you prefer working with VGS, is 1 volt. We're okay. So we'll get 1/2 times K times quantity VGS minus VTH, quantity squared, times 1 plus lambda V VSD, source to drain. So that's where we need to break out our early effect voltage equation to figure, or early effect drain current equation to figure out ID. So we should figure out what region the transistor is operating in. We figured out the early effect. This is greater than the threshold voltage, so it was saturation mode. And then compute VDS and ID given these other conditions, repeat that same procedure. That's a lot harder to do without me like actually writing out the math. I apologize, that's probably confusing. Any more questions about that problem? I tried my best. Again, I don't really have a good way to draw on the screen. Or at least fast enough that I can keep up with my mouth. Okay. Open lecture set 2. So hopefully you can still see my screen. So how do you determine if you want this? The inductor current or the capacitor voltage to be the state variable, in our differential equation. Well, for a parallel circuit, you would notice that, we're using KCl, so we're doing a sum of currents type of idea. So because we're doing a sum of currents, inductor current is the obvious choice. If you try to do capacitor voltage, you will see, you've got to equate a whole bunch of different voltages to each other, and that gets a little bit messy, especially since you're going to be dealing with an integral equation, and we don't deal with integral differential equations. We want purely differential equations. So here, current is the way to go. With the series RLC circuit, we're using KVL, so we're going to want to do the voltage across the capacitor. That is the quick and clean way to do it. Obviously, if you do have circuits that are neither in series or in parallel, you have to make a judgment. Okay, is the output variable we want, first of all, if you can write in terms of the output variable, that's nice. But, is the output device, I guess, whose, equation we're thinking. So if it's a capacitor, how do we write in terms of capacitor voltage? And if it's asking something about the inductor, how do we write in terms of capacitor or inductor current? Does that help you, Aubrey? Good. You're welcome. Any more questions? I was just going to let you know I have a couple things prepared. I have homework 1, problem 3B, the design problem for AJ and anyone else who was interested in seeing that. And I also prepared a switch circuit for those who wanted to see that. Because the switch circuit is a good review of everything in lecture set 2, because you have to just repeat the steps a few times. What do people want to see? You must choose. Which one do you want to see first? Switch. Ooh, looks like the switch wins by a landslide. Okay. I'll make this full screen. Switch circuit. Okay. Then control 1. Okay. Well, for now, we'll do control 1. So here is a circuit. It's a variation of the one in the lecture slides, but it's slightly different. We switched the inductor and capacitor out, and we moved the resistance into the battery branch. So find IL of t, the inductor current, given that switch 1 has stayed down for a long time before switching up at t0 is equal to 0, and switching back down at t equals to t1, staying there for the remainder of time. So for part A, for t less than t0, switch 1 has been down for a very long time. So we expect the circuit is at rest. That's a little bit debatable considering that we just have energy storage devices and no resistance. But, assume it's been down for all of time before time equals 0. So we'll just assume that, the circuit starts at rest. There's 0 capacitor voltage and 0 inductor current. There's no source present in this loop, so that's a reasonable assumption. So for t between t0 and t1, we know the initial conditions are the inductor current is 0 and the capacitor voltage is 0. These quantities cannot instantaneously change. So during this interval, the capacitor remains unenergized, discharged, and the relevant circuit is the voltage source, the resistance, and the inductor all in series. And the capacitor is basically out of the loop, literally. So we need to write a ODE for a series RL circuit. So, well, we're going to have to write what KVL VN equals VR plus VL. Well, VL is just L times DIL dt, and VR is just R times IL of t, where we note that the current through this entire loop is just going to be IL of t. So that's exactly what we get. The input voltage, Vn of t times U of t, as L DIL dt times R times IL of t. Why did I use the unit step function? Well, we've talked about it in convolution lecture, but it represents the sudden appearance of the DC voltage through the action of the switch. Now, if you don't want to think about it, we're only dealing with a time interval where t is greater than 0. So the unit step function is just equal to 1. So if you don't want to throw in the U of t, you don't have to. Are we with me up to the formation of the ODE? I got one yes. I got like 5 yeses. Okay. So now we just go through our normal differential equation solutions process, 4-step process. We form the characteristic equation, we solve the homogeneous solution and write it with unknown coefficients. Then we write the particular solution and solve its coefficients. And then we write the complete solution and use the initial values to solve all the coefficients. So first, the characteristic polynomial. So 0, we said it always equal to 0 is equal to L times lambda, because we got the first derivative here, plus R times 1, because lambda to the 0 is 1. And this is the 0th derivative right here. So we get lambda is equal to negative R over L. So the homogeneous solution is going to be an exponential of the form a times e to the lambda t, where we'll have homogeneous form is a times e to negative R over L times t. And I introduced the U of t. Maybe you don't like the U of t. We're just dealing with an interval where U of t is always 1. So that's fine. Don't write the U of t. It's okay. The particular solution must match our step function input. So we assume it's going to be a step function multiplied by some coefficient. I'll call it b. So the particular solution for the inductor current is b times U of t. We have to put this particular solution into the ODE and solve, considering t is greater than 0. Remember, we put this into the particular solution, we put the particular solution into the ODE. We do not use our initial conditions yet. Save those for later. Some of you get confused about this, but that's okay. We're here to resolve that confusion. So we put this into the ODE. So we get Vn of t is L times the derivative of b times U of t plus R times b times U of t. And we're only considering t greater than 0. So again, those unit steps, they're just multiplying by 1. So we'll get Vn is equal to L times derivative of a constant is just 0. Remember, derivative constants are 0. And then plus R times b. Solve this, we get b is equal to Vn over R. Now we rewrite the complete solution. So we'll say IL of t is our homogeneous part, a times e to the negative R over LT times U of t, plus our particular part, which we said was b times U of t, where b is just Vn over R. So now we have our complete solution. Now we get to use our initial conditions. So now we know IL at 0 plus is A times E to the negative R over L times 0 plus Vn over R, because at 0 plus, this is equal to 1. So we get that 0 is equal to A plus Vn over R, or A is equal to negative Vn over R. So for the solution, hey, both A and B have Vn over R in common. So when we write this out, we can just factor it out. IL of t is equal to Vn over R times 1 minus E to the negative R over LT. And since we're in this time period, we don't need to deal with that pesky unit step function. It's always going to be 1, so why bother writing it out? Now, as part of our switch circuit things, we're not done yet. We only solved, basically half of the problem. The switch is going to flip back down at t is equal to T1. We need to know what the states of our capacitor and inductor are going to be at that point. So we need to know that the inductor current is going to be IL of T1 minus, which is Vn over R times 1 minus E to the negative R over L times T1, where this is all just one gigantic constant, just hard to write out. Are we with me up until where the switch flips back down? I've seen a bunch of yeses so far, so 2K1. I'm glad you think it was a good class. So, okay. So for part C, let's go back to our circuit. The switch has flipped back down. We know that the capacitor must stay at time T1 plus at 0 volts. We've introduced a variable shift where T prime is equal to T minus T1. So the T prime, again, it's not a derivative. It's just a change of variables. It's basically there to, reset all of our equations so that we're dealing with time equals 0 again. Capacitor voltage hasn't changed at time T prime equals 0 plus 0 volts. This is that at IL at T prime equals 0 plus is that, long constant that we just solved for, Vn over R, 1 minus E to negative R over L T1. So during T prime equals greater than 0, the capacitor remains discharged, and the circuit is just a series RLC tank circuit. So, and then the capacitor is going to charge, and the capacitor will discharge, and the inductor will degauss itself, and then back and forth and back and forth. So we need to formulate the ODE using Kcl. So here I'll write Kcl. So here's my node I'm thinking of at the top. What is the total sum of the currents going out? 0 is equal to L times DIL, Currents going out is IL dt, and then plus IC of t. All right, IC of t is just C times dVc dt, but V is shared in common. Vc of t is also equal to VL of t, which is equal to L times DIL dt. So put the two, compose those two functions together. We get LC times d squared IL of t prime dt prime squared plus IL of t prime, where I've been careful to use t prime for my time variable. So I guess I had to amend myself. I was saying t earlier. I should be saying t prime. So again, one more time. We'll use Kcl. IL of t plus IC of t prime equals 0. IL of t prime is just the thing we're going to be used to solve because it's our output. And then Vc of t prime is IC of t prime is just C times dVc dt prime. And then Vc of t prime is just L times DIL dt prime. Long story short, we get this ODE, and it's unforced. There is no forcing function on the other side because there is no source in that loop. It's a homogeneous form. The characteristic polynomial, LC times the second derivative of lambda squared, second derivative becomes lambda squared, and then the function itself just becomes 1. solve for lambda, we get plus or minus j over 1 over square root LC. So if we introduce omega naught equals 1 over square root LC, adding coefficients, the way to write this with purely real functions is ILH of t prime is C1 cosine of omega naught t prime plus C2 sine omega naught t prime. Are we good up to this homogeneous part? We know that when we have purely complex exponentials from homework 2, we should have seen that we get, cosine and sine as our two components. Everyone good? Or do we need to review something? So now, this is normally where we'd find a particular solution. However, there's, no forcing function, so we don't need to find a particular solution. We get to jump a step to the complete solution. It's just the homogeneous solution. So IL of t prime is equal to C1 cosine omega naught t prime plus C2 sine of omega naught t prime. So we solve at time 0 plus. So, and then this is equal to C1 times cosine of 0 plus C2 sine of 0. Sine of 0 is just 0. This cancels out. Cosine of 0 is just 1. So we get C1 is equal to IL at 0 plus, which is Vn over R times quantity 1 minus e to negative R over L times T1. This is just a constant, not a function of time. It just uses T1 in there instead. So now we'll take the derivative of our complete solution. Derivative of our complete solution is negative C1 omega naught cosine of omega naught T prime plus C2 times omega naught times cosine of omega naught T prime, where we use the chain rule to take the derivatives of cosine of omega naught T prime and sine of omega naught T prime. Now, we know that our other initial condition is VC of T prime equals 0 plus, which is equal to L times DDT prime of IL of T prime equals 0 plus. That should say equals 0 plus. But we know this is equal to 0. And then we just solve for this derivative. And then we need to multiply by L. So it's 0 is equal to negative C1 L omega naught times sine of 0. So this term is just 0. Plus C2 times L times omega naught times cosine of 0, which is 1. So we get that C2 times L times omega naught equals 0. That's only possible if C2 is equal to 0. So in this case, we get an entire term going away. So for this time period, we have the following inductor current. IL of t is equal to Vn over R, 1 minus e to the negative R over L T1 times cosine of t prime over square root LC. Or remember, omega naught is just 1 over square root of LC. So we rewrite the complete solution for all time using the inductor current, and t prime is equal to t minus t1. So we have 0 for t less than equal to 0. We have the exponential approach for 0 to t1. And then for t greater than t1, we have this shifted cosine function where we plugged in t minus t1 for t prime. And then cosine has the square root of LC in the denominator. Well, generally we would say omega naught is 1 over square root of LC. And if we're dealing with a damped RLC circuit, then we would have to deal with, defining an underdamped RLC circuit. We would define the damped frequency omega sub d. But, it's pretty universal to deal with this just because it's related to our lambda. Our lambda basically gives us plus or minus j times omega naught. Does that answer your question, Aubrey? Yeah. If your lambda takes on a different form, you might define other things like we did for the, underdamped RLC circuit. And then finally, I plotted the inductor current as a function of time using Vn as 5 volts. T1, when the switch comes back down, is 1.6 seconds. R is equal to 5 ohms. L is equal to 4 Henry. And C is equal to 1 over 900 pi squared farads. Oh, that sounds like a very convenient number. I wonder why that was chosen. You do that, and you'll see for time less than 0, it's 0, like we said. And then we have this exponential approach where you can see this is exponentially approaching Vn over R, or 1 volt. But it gets, interrupted at time 1.6 seconds. And then it starts behaving like a shifted cosine, where here it starts at its height, and then it goes down to negative 0.865 volts, and then back up to 0.865 volts, and so on and so forth. And it's got a period of 7.5 seconds, which is what happens when you do your sinusoid math using omega naught is equal to 1 over square root LC. Does this make more sense than what we did in lecture? Did we learn something new compared to what we did in lecture, or was this just a rehash? Anything more obvious now? You just want to go home and study? Okay. All new for you. Okay. Someone said, I think. That's not as definitive as I'd like. Okay. Well, office hours, I'll start pretty soon. If you want me to go in-person office hours, please send me an email. Otherwise, I'll just do Zoom office hours because, I got a number of things I want to get done today. It is already 10:50, so I need to let the lecture end. So unfortunately, Barat, I cannot do the other example. I will post my document in the solutions part of the right space. So I'll at least put the document up so you can see it. Well, goodbye, everyone. Again, I'll be in office hours soon. You may be asked to plot things. You'll be told what you need to plot. Goodbye.